Yeah, let's discuss about these reactions of phenols in this video from the chapter Alcohols, Phenols and Ethers. Yes, the reactions which are undergone by the phenols are these types. First is electrophilic aromatic substitution, then Coates electrolysis, Riemann-Tiemann reaction, reaction with zinc dust, and oxidation. Yes, let's look at one by one in detail. Now, the first one is electrophilic aromatic substitution. Yes. First, look at benzene now. This is benzene. See, this benzene, what type of reactions it will undergo? So this benzene is electron rich because this pi electron cloud, this is electron rich. So it will undergo the electrophilic substitution reactions. That means the E plus can attack easily on this, and it's a substitution reactions which are taking place. It's electrophilic substitution reactions. And when we come to phenol, yeah, so phenol will also undergo this electrophilic substitution reactions. Right, but when we, yes, these are also undergoing what? Electrophilic substitution reactions, but which is more reactive towards this electrophiles, whether it is benzene or phenols. Let's look at them. See, this oxygen has lone pair of electrons on it. So this can donate the lone pair of electrons into the ring by means of what effect? Plus M effect. That means they are in resonance with the ring. As a result of which, the electron cloud on the benzene ring will increase. So it will increase. So it's now very easy for the electrophile to come and attack on this, or because there is the electron cloud is increased. That means it has become electron rich when compared to that of this benzene. So it is easy for the phenol to undergo the electrophilic substitution reactions when compared to that of this benzene. So we can say that is OH is an ring activating group. So it's what? Ring activating group, because it activates the ring towards electrophilic substitution reaction. So it's a ring activating group towards what? Towards electrophilic substitution reactions. And yeah, substitution reactions. And when we look at this resonance structures here, so where is the negative charge localized? Right, is either at ortho or the para positions, they are becoming electron rich. So it is easy for the electrophile to get substituted at ortho-para position. So OH is a ring activating group and it's ortho-para directing group. In general, the groups which are ring activating groups are ortho-para directing groups, and ring deactivating groups are meta directing groups, except for that of chlorobenzenes, that is halo arrays. There, even though it is a ring activator, that is a ring deactivator, that is ortho-para directing. But generally, the ring activating groups are ortho-para directing groups, because when we look at the resonance structures, we see that the negative charge is at ortho and the para positions. So it's easy for the electrophilic substitution to occur at ortho and the para position. Right. This is about this phenol and where this electrophilic substitution reactions will occur. So the general type of electrophilic substitution reactions that phenols will undergo, same, that is nitration and halogenation. Right. When we look at the nitration here, yes, here, yeah, the phenols can undergo this nitration reactions with dilute HNO3 at 298 Kelvin. The reactions are different when compared to that of this concentrated HNO3. Yes, when this phenol is made to react with dilute HNO3 at 298 Kelvin, we get the mixture of ortho and para-nitrophenols. Right, ortho-nitrophenol and para-nitrophenol here. We'll get a mixture of it. Yes. Now, when we are carrying out the reaction with concentrated HNO3, this is dilute HNO3 at 298 Kelvin. This is what? Nitration of phenols, right? We'll get what? Ortho and para-nitrophenols mixture. But if you carry out the reaction with concentrated HNO3, here we'll get what? a 2,4,6 trinitrophenol, which is called as picric acid here. So the products are different when we are changing the experimental conditions or changing the concentration of nitric acid here. So with dilute HNO3, it is mixture of ortho and para nitrophenols. With concentrated HNO3, we are getting 2,4,6 trinitrophenol. Yes. Now, when these are having different boiling points, that is ortho and para nitrophenols, what their boiling points are different. So they can be separated by means of steam distillation here. Why their boiling points are different, or why they are, how can they be separated by steam distillation? So when we look at this, there is a hydrogen bonding, that means in between these groups, OH and N groups, the H of this and NO of this, this is called as intramolecular hydrogen bonding, right? Because within the molecule, we can see this hydrogen bonding. But when we look at this, there's intermolecular hydrogen bonding in para-nitrophenol. So how can you show this? Let me, this. So this is what is happening. That means intermolecular hydrogen bonding can be seen in this. Yes. So this, in order to break this, this is what intermolecular hydrogen bonding. But here, intramolecular hydrogen bonding. So in order to break these bonds in between the molecules, and then that will become volatile, right? Then it can enter into the vapor state. In this case, the temperature required is more in order to boil this, in order to break these bonds. But here, since in between, in the same molecule, that is intra, the boiling point is less here. So because of the difference in the boiling point, because of this difference in the hydrogen bonding, that is intra and intermolecular hydrogen bonding, this is less volatile, that is para-nitrophenol, and this is more volatile. As a result, they can be separated by means of steam distillation. Right. Then, when we are carrying out the reaction with concentrated HNO3, we are getting what? 2,4,6 trinitrophenol, but the yields are low here. Yields are low. So, in order to improve the yield, what do you do here? First, treat this phenol with concentrated sulfuric acid. So we get 2,4-disulfonic acid, phenol 2,4-disulfonic acid, phenol, this is 2,4-disulfonic acid, right? 2,4-disulfonic acid, which on treatment with concentrated HNO3 will give you picric acid. This particular picric acid, okay? So in order to improve the yield, what do you do? First treat it with concentrated sulfuric acid and then with concentrated HNO3. So we can improve the yield by this process of, we can improve the yield of picric acid, right? Then, yes. Right. Next one is halogenation. As we are seeing how these nitration reaction is occurring, this halogenation, right? Halogenation, this Br2, when it is treated in the presence of aqueous medium, that is Br2 in the presence of water, will get 2,4,6 tribromophenol. But when phenol is treated with bromine in the presence of low polarity solvents like chloroform or CS2, also we get mixture of, again, orthobromophenol and parabromophenol. This parabromophenol, we think, we know it is a major product and this is a minor product. Right. Here we are not using FeBr3, that is a Lewis acid, right? So the use of this Lewis acid is not necessary. For benzene, for the halogenation reaction to take place, we are using this, FeBr3, that is a Lewis acid, because this activates the ionization of Br2 to Br plus and FeBr4 minus, and then the attack of the electrophile can occur. But here there is no need of Lewis acid, because no Lewis acid is needed, because I said this OH is activating group. So it activates the ring so much that Lewis acid is not needed for the ionization of Br2. Instead, the phenol ring, I mean the benzene ring itself will initiate the ionization of Br2 to Br plus and Br minus. So no Lewis acid needed here for the reaction to proceed. But here for halogenation of benzene, the Lewis acid was needed. But here, because its reactivity is more because of the presence of OH, no Lewis acid is needed to initiate the reaction. Yes, this is about the reactions of phenols. The first one, that is electrophilic aromatic substitution, and the rest of it I'm going to discuss in the next video. Yeah. Trainings are also given from this Isha Chem Academy, and the details of this has been given in the description box below. And yeah, if you like this, please do like, share, and subscribe my channel. And if you want any video to be made, particularly, comment in the comment section. Yes.